Now let's see dynamic partitioning or variable partitioning. It has got some advantages over fixed partitioning, and it is the next to this static partitioning, that fixed partitioning, dynamic partitioning is widely used. So just watch it. I'll tell you what it means. So till now we have seen this static partitioning, right? So in static partitioning, what happened was, see, if this is the memory and some part of it is already dedicated to OS, then what we did is we have partitioned the remaining space like this, maybe 2 kb, 4 kb, 16 kb, something like this, 32 kb, something, right? And now any process which wants to come into the main memory, we are going to put it in one of the partitions. But the problem there was, if a partition size is 4 kb, let us say 2 kb, right, and if the process which has come is 1 kb, then I am going to put the process in 1 kb here, and 1 kb is going to be remaining, right? And because of that, this 1 kb is wasted. See, the main rule is this: either in dynamic partitioning or static partitioning, the rule is always a process has to take one partition completely, and it cannot span over two partitions, or we cannot put two processes in the same partition. So even though 1 kb of space is remaining here, that we cannot use. That is called internal fragmentation. Maybe if you could think of a cake example, let us say we have a cake, okay, and now we have already cut it into pieces like this, right? So anyone who wants to have the cake should take one piece. That is the rule, right? But then what happens is, someone might be on diet and he might not want to have the full cake. Maybe someone would be trying for a 6-pack. Okay, in computer science we should not try for 6-pack, we should try for 8-pack, isn't it? Why? Because 8 is a power of 2, isn't it? In computer science everything has to be a power of 2. 2 power 3 is 8, isn't it? So let us say, you cannot take the big piece because you are trying for 8-pack, and even if you take this entire piece, you will just have a bite and waste it all. Then what is the other solution? Leave the cake as it is, like this, right? And let the user, whoever wants the cake, let him cut it. So you don't decide about this size, so just hand him over the knife, and whatever piece he wants, he'll cut it. If you want a small piece, he'll cut it like that. Got it? And that is the main difference between fixed partitioning and dynamic partitioning. This is fixed partitioning, which means the sizes of partitions are already fixed, and either you like it or not, you have to take one partition, right? Even if it is big for you, right? And sometimes what happens is, the problem here is some people might want bigger than this, but then the rule is anyone can take only one piece. Because of that, they might fall short. So the dynamic partitioning is, if you want a smaller one, you can take it. If you want a large one, yes, you can take it, right? So if you want this piece, you take it. If you want this piece, you take it, right? That is how dynamic partitioning works. So what I mean to say is, if you have the memory like this, and one part of it is for operating system that we are not going to touch, the remaining space, which is also called as user area or user space, right? So this entire part, we are not going to make it into partitions. Let the process come, then I am going to create a partition. Now the partition will be equal to the process need. Then what happens? There is no wastage at all. Let us say now a process has come, its requirement is 1 kb. Fine, good. I'll just create new one partition whose size is equal to 1 kb, and I'll put it completely there, right? Therefore there is no internal fragmentation, right? Very important. So if I go for dynamic partitioning, there is no internal fragmentation, which means you can completely fill up this space without any wastage, right? So there is some confusion here, right? What is external fragmentation? Generally, one definition is one definition. I am talking about one definition. External fragmentation is, because of internal fragmentation, if there is some wastage in the memory, and if all the wastage put together is making up some size, right? I told you there. So let us say here 1 kb is wasted here, 1 kb, 1 kb, 1 kb, 1 kb. If in all the partitions, let us assume that 1 kb is wasted because of internal fragmentation, then how much is total wastage? 1, 2, 3, 4, 5. 5 kb is the total wastage, right? So external fragmentation is, even though we have 5 kb memory available at different places, we will not be able to use it because we had a rule that the process has to be contiguous, right? And process cannot be kept 1 kb here, 1 kb here, 1 kb here, 1 kb here, and moreover one partition can hold only one process, right? So if there is internal fragmentation, there is definitely external fragmentation, isn't it? If there is internal fragmentation, there is definitely external fragmentation, right? Are you following it? I think you got the reason, right? Whenever there is internal fragmentation, we will not be able to use that space even though the space is available. That is external fragmentation, right? But then if there is no internal fragmentation, you cannot say that there is no external fragmentation. That is very important. I'll just show you how it is possible, right? See, what I mean to say is, now whenever a process arrives, I am going to dedicate it the partition, or I am going to create a partition whose size is equal to that process, and therefore I am saying that the process is there is no wastage inside the partition, so there is no internal fragmentation. Fine. Now what happens? Assume that here it has, a process has taken 1 kb, right, and next process has come and it has taken 2 kb, and next process has come and it has taken 3 kb, something like this, and next process wanted 5 kb and we dedicated this 5 kb to this, right? And now assume that, and at some point this 1 kb process has run to completion, and therefore we have freed it up, which means we have removed the 1 kb process from this, and now 1 kb is available, this block is available, right? And this 3 kb is also freed up, and therefore this 3 kb is also vacated. This process which is there is pulled back, and therefore these two partitions are available now. So 1 kb is available and 3 kb is available. Are you following it? See, initially I have given the process 4 processes like this, and 2 processes have run to completion, and therefore I pull them back, right? Now there are empty spaces. One space is equal to 1 kb and other space is equal to 3 kb, right? Therefore what is the total space available now? 4 kb. 4 kb of free space is available. Now even if a process with 4 kb comes into play, and even if it wants the 4 kb, we will not be able to dedicate, or we will not be able to give 4 kb for it, because it is not contiguous, right? So here also there is external fragmentation. Why? Because we have free space available at 2 points, as 2 parts, and since they are not contiguous, we are not able to dedicate it to, assign it to any process. That is called external fragmentation. Even though there is no internal fragmentation, there can be external fragmentation. So what is the reason for external fragmentation? So the main reason for external fragmentation is your rule saying that a process has to be contiguous, right? It cannot occupy various places. So if you have to have no external fragmentation, change your rule, or you say that a process need not be present contiguously. That is called paging. We shall see it later. Okay, so the main reason for external fragmentation is not internal fragmentation. People think that because of internal fragmentation there is external fragmentation. No, that is not true. But then if there is internal fragmentation, there will be external fragmentation. That is fine. But even if there is no internal fragmentation, here there is external fragmentation. And how are you going to what is the main culprit here? The rule that a process has to be contiguous, right? So if you can break that rule, if you can say that a process can be present as parts in various partitions, then you can say that there will be no external fragmentation, and that is what where we are going. That is where we are going to use paging. But before going to paging, maybe we could try to solve it in some other manner. Watch it. Maybe before going to that paging, let's try to solve it this way. There is a gap here and there is a gap here, and these two gaps are not being dedicated to any a process of 4 kb because it has to be contiguous. Then what I do is I apply a method called as compaction. Compaction means pulling all the occupied parts together and pulling all the free parts together, right? So if this 2 kb and 5 kb are occupied, I am going to pull 2 kb and 5 kb together, and I am going to pull 1 kb and 3 kb together. Therefore if I do that, if I pull them, then the free space will be available at one place. So what is compaction? It is called as compaction, or some textbooks they even call it as defragmentation. So both are the names, but anyway the process is like this. You pull the occupied spaces together and you pull the free spaces together, so that the entire free space will come as one big block, and that could be dedicated to any process because now it is contiguous, right? So that is the method, that is the solution for now, as of now. Later we have paging. Paging will solve this. In paging there is no compaction required, right? But then as of now we can solve it using compaction, but compaction has got its own disadvantages. So one disadvantage is when you are moving these processes around, which means when you are pulling this, like this, when you are moving the process up and then free space down, the entire procedure, all the processes have to be stopped for some time because you are doing some work, isn't it? And now that is actually a copying operation in memory. We are going to copy the memory bits, right? I mean the data in memory from one place to the other place. So if you think that, let us say the problem is, in order to copy 4 bytes, if we need 4 nanoseconds, or let us say in order to copy 1 byte, if we need 4 nanoseconds, right? Then if the total memory is 256 MB, right, then it nearly takes how many? You can just multiply with this. 256 into m is, let us for now assume that m is 2 power something, 2 power 20, into 4 into nano is 10 power minus 9, right? So it is going to be a considerable amount of time. So what I mean to say is, whenever you have any memory like this, a very large memory, in order to do compaction, it is going to take some time, which is not very small, which will be in seconds, not in nanoseconds or milliseconds, right? So all that time the CPU is going to be idle. Therefore the efficiency of the system is going to come down because of compaction. So even external fragmentation is not a good solution either. Internal fragmentation has many limitations, like the static fragmentation or fixed partition has many limitations, like internal fragmentation, external fragmentation, and limiting the degree of multi-programming and all these, right? And therefore we are using external fragmentation, but external fragmentation also has got one limitation, which means this compaction, right? So as even though it has got some limitations, it has got some advantages as well. Let's see the advantages of this external fragment, this dynamic partitioning. So dynamic partitioning or variable partitioning has got some advantages. One advantage is it is flexible in the sense the degree of multi-programming is not fixed, isn't it? So degree of multi-programming. What is degree of multi-programming? The number of processes that can be present in the system at any time, right? It is not fixed, it is dynamic. So depending on the sizes of the processes, right, at every time, at every point of time, the number of processes that can be present in the memory are going to change. That is dynamic, right? And moreover, there is no limitation on size of the process, right? So size of the process is not limited, by size of a partition, isn't it? Earlier, if a partition was of some size, you are supposed to use only one partition, therefore your process size is limited. But now it is not limited by the size of the process, it is limited by the total available free space, isn't it? So these are the advantages when we go for dynamic. So number of processes that can be present and the size of each process, they are going to be varying, and degree of multi-programming is going to be varying, and there is a lot of flexibility. Any process can be loaded at any point, isn't it? But along with this flexibility, right, we get lot of problems as well. The problem is earlier when it was static partitioning or fixed partitioning, there is only one list of partitions, and that list doesn't change. Let us say we had this 2, 4, 16, 32, 64. This list was there like that, and it never changed. But now using this dynamic partitioning, the list of free spaces and the list of used spaces both are going to continuously going to vary, right? For example, see this, watch it. So initially we have completely one free. Okay, the problem is this. Why should we do this is, I'm talking about disadvantages. Disadvantages of this dynamic partition is allocation and deallocation. Allocation and deallocation of memory is complex. It is going to be very complex. The reason is initially there is one contiguous free space available, right, a big free space, and later when we fill them up with these processes and the processes are moving out, they are going to create some holes. The terminology is holes. What is a hole is whenever a process is occupying a particular amount of memory and then suddenly it moves out, that particular slot is going to be a hole. I mean, that is a vacant slot, right? So because of this vacant slot, the problem is that, you know, when we are having, let us say a process is here occupying 1 KB, and when we pull it out, there is going to be a hole created, right? So because of that hole, you know, the management is going to be very difficult, because as a period of as we you know as we have done this process for, let us say, for some time, the number of holes created will be very high, and now the managing all the holes is going to be a headache, right? So here how many holes are there, or how many partitions are there? 1 2 3 4 5. So managing five partitions is very easy, right? Maybe you could have an array containing 5 elements, and each array will say whether it is occupied or free, and therefore it is very easy, right? But then here management is going to be very difficult, in the sense as the time grows, you know, the number of partitions, they keep on changing dynamically, and the number of holes will get created and some holes will get managed, and therefore the management is going to be really a headache, right? And after managing it, see, keeping track of what are the holes and what are the processes is one thing, fine. And the second important thing is, how are you going to allocate and deallocate, which means what are you going to do whenever you are going to, you know, assign a hole to a process, and whenever a process vacates, right? Either it will lead to creating a new process or creating a new hole, isn't it? Therefore it is going to be really headache. So there are various data structures which are used in order to keep track of what are the holes and what are the use spaces, first thing. And then there are various algorithms used on these data structures in order to allocate and deallocate the memory, right? So we shall see now what are these, how to keep track of this entire how to manage all the holes and all the processes, one thing. And second thing is, using these data structures used for management, how can we allocate and deallocate the memory? We shall see that now. Okay.